Hello everybody. On today's episode we're talking about vertical forces. Our essential question: how do we apply Newton's second law to analyze a situation? We've already talked about Newton's first law in that any object requires a net force for it to not be moving at a constant velocity. Here's our objective preview. What we're going to be doing, we're going to be looking at Newton's second law, including what net force is and how forces change motion. We're going to apply Newton's second law to situations where the objects move vertically. There's some pages, and then you guys don't care about that. All right, vector sum is the adding up of a set quantities that have direction, but where some of the quantities are positive or negative depending on their direction. We've been doing this all year. We're just formalizing it now to be something a little bit closer to math, maybe that you've seen in Algebra 2. Inertia is a property of an object that resists changes in motion. Inertia is effectively the same thing as mass, not a force, but mass. Here we go. Unbalanced forces cause acceleration. That's Newton's second law in a nutshell. That's it. Have you ever noticed that all objects, regardless of their mass, fall together with the same acceleration? Yes! Yes! We've done that, right? Hopefully. And we've also seen the moon drop, where we dropped a feather and a hammer, and they fell at the same rate. Hopefully you have, since that was a major idea 3 lessons ago. Have you ever noticed that you feel heavier in an elevator at certain times and lighter at other times? We can use Newton's second law to explain these ideas. Newton's second law says an object's acceleration is directly proportional to the vector sum of all forces acting on the object and inversely proportional to its mass. Lots of words, let's break it down. Acceleration, how velocity changes over time. Vector sum is the sum of all forces. We add up all of the forces, treating forces in opposite directions as positive and negative, right? We've been using right as positive, up as positive, down as negative, left as negative. We call this net force for short. Directly proportional. When the net force increases, the acceleration increases by the same factor. That is a very specific word. If we were to look at that on a graph, it would be a linear graph that goes through the origin. If it doesn't go through the origin, it's not directly proportional. Inversely proportional. Greater masses will receive less acceleration from the same net force. There it is in equation form. Acceleration. This sigma here, remember, means the sum of. So the sum of your forces divided by mass. It's not just F. It is the sum of your forces. Acceleration is on the left because acceleration is the dependent quantity, known as the effect. Net force and mass are on the right side of the equation because they're independent of each other. They are the causes. If you change force here, if you increase force, it's going to increase acceleration. If you increase mass, it's going to decrease acceleration because it's in the denominator. Greek letter sigma means sum. The arrow over the top of A and F remind us that acceleration and force are both vectors. We can instead write the equation with F net rather than sigma F, as long as we promise that we know that F net means to add up all of the forces that act on an object, but treat the forces as positive or negative. For this, I want you to remember a phrase. And this phrase will help you along, I think. Let's see. F net. What that means is the stuff that makes it go and by it, I mean whatever is the object we are looking at, minus the stuff holding it back. Now you don't specifically have to, if this seems stupid to you, stuff, not a real physics word, Mr. Scapettes. I understand. This will make it so dealing with the positive and negatives is a lot easier, because the stuff that makes it go is going to be in the positive direction. The stuff holding it back is going to be in the negative direction. This is just an alternative way. Stuff holding it back all of that, if we solve this equation by multiplying m on each side, equals mass times the net acceleration. That says net. So the net force is just the stuff that makes it go minus the stuff holding it back equals mass times acceleration, whereas acceleration is your net acceleration. Okay? That's one way of doing it. Let's keep going. We can write this as long as we remember that acceleration depends on the force acting on the mass that they act on. We remember that force and acceleration are both vectors. So this is just condensed. Like, this is normally what you would see. Well, like if you've ever learned Newton's second law in another class, physical science, middle school, anything like that, it would just be F equals ma, which is unfortunate. It's not the whole story. If a big net force acts on an object, the object will have a great acceleration. Right? So if we have a big force, the acceleration gets bigger. If a small force acts on an object, then the object will have a small acceleration. If a net force acts on a big mass, that object will have a small acceleration. If a net force acts on a small mass, that object will have a great acceleration. On your equation sheet, this is what it's going to look like. Sigma F over m equals F net over m. I know your equation sheet looks different than this, but I promise you, it's going to look just like this. Inertia. Sometimes we refer to mass as inertia. Inertia is an object's resistance to change its motion. Very massive objects have lots of inertia, and it's very difficult to speed them up or slow them down. Small mass objects have less inertia, and it's easier to speed them up or slow them down. Inertia is, again, not a force. Inertia. So that means, when I say it's not a force, that means it's not going to show up on a free body diagram. Absolutely not. Inertia is a property of an object that is the same as its mass. We'll do some problems on the next episode.